Okay, so I think everybody got the same answer that I did. X is 0.03 molar, pH is 1.5. Now, the goal is that we do not solve quadratics in this class on a regular basis. That's not the goal of the class. Most of the math we're going to deal with, you don't have to do that. So now let's look at another way that we can explore the strength of an acid. In Chem 111, we said strong acids dissociate completely, weak acids dissociate a little bit. Now, using equilibrium discussions, we can figure out what the hydrogen ion concentration is. But another way to compare things sometimes is just talking about percent. We know that from everyday life, parts per 100. So we can talk about the percent ionization, and in this case, we calculate the percent ionization by looking at the hydrogen ion concentration at equilibrium divided by the acid concentration at equilibrium, and then multiplying by 100. And we can think of that as the amount ionized, because whatever the hydrogen concentration is, that's how much of the acid broke apart, divided by the amount initially, because it's usually the same with sig figs, times 100. So let's look at an example. What's the percent ionization of acetic acid in 0.20 molar acetic acid? So we know the amount available initially, 0.20 molar. Now we can calculate the amount ionized using an ice chart. So we know it's acetic acid, so we'll also go look up the Ka, 1.8 times 10 to the negative fifth. Now our initial concentration, 0.20 molar, 0 and 0 for H plus and A minus. This goes down by X minus X plus X plus X. At equilibrium, 0.20 minus X, X, and X. Now, looking at this, we have a Ka of 1.8 times 10 to the negative fifth. We have an initial concentration that's reasonably large, 0.20. So we can assume X is small, and this is about 0.20 molar. So we know that our Ka will be equal to H plus times A minus divided by HA. So now we plug in the numbers. 1.8 times 10 to the negative fifth is equal to the hydrogen concentration, X, times the acetate concentration, X, divided by the acid concentration, 0.20 molar. Now we rearrange and we get 3.6 times 10 to the negative sixth is equal to X squared. So X, which is representing for us the hydrogen ion concentration, is equal to the square root of 3.6 times 10 to the negative sixth. And that is equal to 1.9 times 10 to the negative third molar. So now we ask ourselves, is X small compared to our initial concentration? We had 0.20 minus 0.0019. So indeed it is small, and it was a good assumption to make the math easier. So now from this we could find the pH if we wanted to, but that's not what we're doing here. We're finding percent ionization. So we have percent ionization is equal to the hydrogen concentration divided by the acid concentration, 1.9 times 10 to the negative third molar, well, times 100, divided by 0.20 molar times 100, and that is equal to 0.95% ionization in 0.2 molar. So, again, we've said it's small. That's small. It's less than 1%. Okay? Go ahead now on your whiteboards, and these are two different problems. Find the ionization in these two different concentrations of the same acid, acetic acid.